Dear students, already we have discussed hydrogen bond in the last part. Now we are going to discuss about some example where hydrogen bond has important applications, which will change some properties abnormally, especially boiling point, and of course, intramolecular hydrogen bond stability abnormally increases. That I'm going to give example. And that examples are very important with respect to our competitive exam. First example, we'll do compare her boiling point. Boiling point. Boiling point of different molecules. Take ammonia in the group 15 hydrox pH 3, ASH 3, SBH 3, and BIH 3. I have taken here group 15 hydrides. No doubt the group nitrogen, phosphorus, acid, antibody, bismuth. These are mostly covalent. And for covalent compound, boiling point depends on intermolecular attraction. That intermolecular attraction is controlled by van der Waals. And van der Waals force depends on surface area of the molecule or site. If I take only the van der Waals of this covalent hydride, then BiH3 by quite should highest since its size maximum. Then SBH3 and minimum NH3. But in NH3 there we get the intermolecular hydrogen bond. Nitrogen of one ammonia molecule will make hydrogen bond with H of another ammonia molecule, which will increases the intermolecular attraction, which will increases the association. That's why boiling point ammonia is abnormally higher. But the position of ammonia, you have to remember it, not highest. Here you will get in between this sets and this sets, the position of ammonia. The boiling point here, Bi is 3, maximum psi, little bit ionic also, since bismuth has a metallic character, greater than SBH3. And here is the and before pH3 and ASH3 due to hydrogen bond, remember, and greater than ASH3, arsenic hydride, greater than phosphate. Phosphate, you know those. This ammonia position greater than ASH3 at pH3. Remember, it is due to hydrogen bond. Due to intermolecular hydrogen bonds, of course, intermolecular hydrogen. Now, next example, a blue 16 hydride, H2O, H2S, H2SC, H2PE, teromere hydride. And if I take size or van der Waals attraction, this is highest, this is this. But remember, here we get effective hydrogen bond that one water molecule can make maximum 4 number of hydrogen bond. Since I told you, this oxygen will form 2 number of hydrogen bonds since it has 2 load pair of electron, and this hydrogen also form 2 number of hydrogen bond. One water molecule maximum it can form 4 number of hydrogen bond. Now due to hydrogen bond, its boiling point abnormally highest. That means the order of boiling point, water greater than, others are normal on the basis of size, H2SC and H2S. So here, water abnormally highest boiling point due to hydrogen bond, intermolecular hydrogen bond. And water is life. Since water is liquid, that's why you can say hydrogen bond is life. If there are no hydrogen bond, then water they are liquid. Due to hydrogen bond, due to strong cohesive force, it is liquid. Now, third example, boiling point. Third example, I'm taking halogen hydride, HF, HCl, HBr, HI. Now, on the basis of fight, HI should highest, HF should least, but the boiling point of HF abnormally highest due to effective intermolecular hydrogen bond. HF greater than HI greater than HBr greater than HCl. This abnormally highest due to intermolecular hydrogen bond. Now, another example of boiling point. Simple if I do compare H3PO4 and H2SO. You know the structure, density or boiling point if I do compare. Intermolecular hydrogen bond between H3PO4 molecule, they will get 3 number of hydrogen bond between H3PO4 molecule, since there are 3 OH. You know this, all 3 hydrogen in a structure exist as OH form. Here 2 OH. More number of intermolecular hydrogen bond. Here less number of intermolecular hydrogen bond. That's why boiling point of phosphoric acid greater than sulfuric acid, as well as density of phosphoric acid greater than sulfuric acid. Hydrogen bond friend, he explained this phenomena. Now the fifth example, organic molecule, you know, orthonitrophenol. Ortho 1-2 position is ortho. Put a nitro group, orthonitrophenol. And take paranitrophenol. This is paranitrophenol. Paranitrophenol. What food position is para? I think organically same parallel you will see there, parallelly both put up to the fall. But remember, here you will get intramolecular hydrogen bond between H of OH and oxygen amino. Here no question of intra. Only inter possible. Inter. That means this H will make hydrogen bond with another molecule of paranitrophenol. This oxygen will make hydrogen bond with another molecule of paranitrophenol. That is intermolecular hydrogen bond. But here H of OH involved intramolecular hydrogen bond. That's why later it will participate in DAF. And it will isolated molecular stability increases, but the boiling point, you know, increases due to intermolecular hydrogen bond. Boiling point of this one greater than this. One more thing I will discuss here, although it is not the part of boiling point, acidic strength. See, when I do compare the acidic strength from the GOC application, you know it to group is so strong minus air effect, minus mesomeric effect. Here also you will see the minus mesomeric effect. Mesomeric effect will operate at ortho and paradic to conjugation. At beta all inductive will operate. And you know mesomeric with respect to OH close is ortho and far away that is para. That means mesomeric effect more effective at ortho than para. And you know minus M effect or any withdrawing effect always increases the acidic strength of the hydrogen. If I do consider only the mesomeric effect, that will give this orthonitrophenol should more acidic than paranitrophenol. But remember, acidic strength of paranitrophenol get up than orthonitrophenol. How this exception you got? It is not the exception. You have to consider intramolecular hydrogen bond. This intramolecular hydrogen bond will reduce a little bit acidic strength of this hydrogen. This hydrogen bounded by additional hydrogen bond. That's why slightly more energy required to leave or to deprotonate. That's why its acidic strength slightly less than para. This is additional part I have discussed here. Similarly, if I take orthohydroxybenzyaldehyde, orthohydroxybenzyaldehyde, that is called salicylaldehyde. Here you get intramolecular hydrogen bond, and this is para-hydroxybenzaldehyde, no question of itra, only inter. It's automatically boiling point of this one greater than this. In organic reaction, when parallelly these two products will form, since their boiling points are different, you can easily separate them by steam distillation or fractional distillation method. You know fractional distillation method. You can apply if their boiling points are different. Here boiling points are different due to hydrogen bond. Here you will get intra, or here you got intramolecular hydrogen bond. Here intermolecular hydrogen bond. Now, like this, so many examples you will get in organic chemistry where there are intramolecular hydrogen or they are boiling point less, but a stability of the isolated molecule more. And if there are intermolecular hydrogen bond, that will increases the boiling point. Now I'll discuss another thing, which is the another application of hydrogen bond that I have discussed in conformer part. Then you got more stable than anti due to hydrogen bond. See that part of my video where I have discussed the different conformers of butane derivatives. Now, I do compare acidic strength. Now, acidic strength, where hydrogen bond will play an important role. Acidic strength. I'm taking first example of acidic strength. You know, fumaric acid and malic acid. These two are isomer to each other. You know, C is malic acid. This is malic acid, malic acid. This is C's isomer. And trans is fumaric acid. This is fumaric acid. Trans isomer. Now, if I do compare which one more acidic, can you tell which one more acidic? Malic acid is more acidic. Why? Question answer we give hydrogen bond. Hydrogen bond will explain its fine. How? See, if it will lose one proton, you know it is a dibasic acid, one is K1, K2. The conjugate base is this. And conjugate base will get additional stability. Conjugate base will get additional stability due to hydrogen bond, intramolecular hydrogen. This hydrogen will make it more stable. And you know, if conjugate base is stable, then its corresponding acid is strong. But here's no question of intramolecular hydrogen bond. That's why the acidic strength of malic acid greater than fumaric acid, although they are geometrical isomers. Next example. Also regarding the acidic strength. See, if I take this salicylic acid, orthosalicylic acid, carboxylic acid, put OH group at ortho position. Second example. Now, let me say, be it put OH at beta, carboxybenzoic acid derivative. It is benzoic acid, COH, take OH at meta position. 1, 3 is beta. And the last one, take OH at para position. Para-hydroxybenzoic acid. If the question is to compare the Ka value or acidic strength, and pKa value order will be reverse order. Now tell me which one is more acidic. I told you at meta only minus I is occurring, which will show minus I. At para they will get strong plus mesomeric effect. At ortho also plus mesomeric effect. And you know, another effect decreases the acidic strength. And you know, an ortho-mesomeric effect is more dominating than para. If I take only the mesomeric effect and inductive, then it should least acidic than this, and most acidic is meta. But remember, the order is not correct. If You take only mesomeric and inductive. Here, hydrogen bond will play an important role. Actual acidic strength order is A greater than B greater than C. Surprisingly, see how A first B greater than C that you got, since here minus I operate, withdrawing increases acidic strength, this will decreases the acidic strength. It has no problem, no confusion. But how A is highest? That is magically explained by the hydrogen bond. Similarly, take conjugate base. This is the conjugate base of benzoic acid and orthohydrogen. Finally, this conjugate base will make an effective hydrogen bond with ortho-H upon H, which will increases the stability of conjugate base. If conjugate base is stable, then it will readily release its proton K increases, acidic strength increases. That's why here intramolecular hydrogen bond abnormally increases the acidic strength of orthohydroxy benzoic acid. Next example. One thing I want to mention here, when I have given the example of orthonitrophenol and paranitrophenol, there also hydrogen bond. There was also hydrogen bond, but that hydrogen bond reduces the acidic strength. But here hydrogen bond increases acidic strength. Since here the effective hydrogen bond with conjugate base, but there the hydrogen bond was with the acid. That hydrogen is additionally bounded by the hydrogen bond. Difficult to release, that's why K reduces. Now, another example of hydrogen bond, not acidic step. I'm going to give another example. You know, washing soda, blue vitriol. Blue vitriol, you know, CuSO4, dark fine water. You know, due to this high crystalline water, it is blue in color. And if there are no crystalline water, it is colorless. And this color due to complex salt that you will get in complex coordination compound chapter. Now, if I give heat or if you keep it in open here, easily 4 moles of water are removed. Go to the air. But to remove this last water molecule, strong heat is required. Why? Hydrogen bond will give you the answer. See the structure. Actually, the structure is CuH2O whole 4. These are coordinately bonded with the copper 2 plus. Here the counter ion is sulfate. Sulfate. I'm drawing here sulfate. Sulfate is counter ion. This is 2 plus. And here it is 2 minus. And the last water molecule, this water molecule attached or bonded through effective hydrogen bond. Through effective hydrogen bond. To remove this water molecule from the blue vitriol, you have to supply additional heat since there are hydrogen bond. That's why to remove the last water molecule, strong heat is required. Similar phenomena you will get it washing soap, Na2CO3 dot 10 water. If you keep in open air, normally 9 moles of water removed, but the last water molecule difficult to remove, there you have to supply strong heat. Since the last water molecule attached through the hydrogen bond with carbonate. The hydrogen bond has important role. You will get it different organic chapter, biomolecules, great application of hydrogen bond. Now, another application, simple application. Total organic chemistry has application. In organic chemistry, biochemistry has application of hydrogen bond. You know, unique 3D shape of protein due to hydrogen bond. Now we know chloral. chloral, the structure CCl3, Cl3, CHO. This is chloral. Normally, aldehyde exists as this. This is anhydride form. But it has another form. If you take water molecule, then C double bond O converted to 2 OH group. This one. Now this chloral 100% exists as this form, not as this anhydride form. Normal, not like normal aldehyde. It will exist as this form. Now question will arise, why it will exist as this form? Due to hydrogen bond. Here the hydrogen bond surprisingly with chlorine. Chlorine also form hydrogen bond, but chlorine is bulky inside. The overlap is not effective. That's why its corresponding energy not 20 kilojoule per mole. Its energy near about 10 to 12 kilojoule per mole, and there is enough to stabilize the hydrated form of chloral. The chloral exists as hydrated form 100% due to this intramolecular hydrogen bond that will increases the stability of the hydrated form. So many examples you will get in organic chemistry. They are hydrogen bond intermolecular as well as intramolecular will change the property abnormally. If you consider the hydrogen bond, then you can explain that abnormal phenomena that I have discussed in conformers. Also, one thing remember, hydrogen bond, basically intramolecular hydrogen bond that will increases the stability of molecule, and intermolecular hydrogen bond that will increases the stability of the whole system, that will change the property of the whole system, that is like boiling point, volatility decreases. Now, the structure of ice. Ice. Can you tell me? Ice, density less than liquid water. How? I told you hydrogen bond is a directional bond. Actually, in ice, plus water, tetrahedral sp3 hybridized. 4 number of hydrogen bond you will get. This side one hydrogen bond. This side one hydrogen bond with one water molecule. This side one hydrogen bond with one water molecule. This side hydrogen bond with one water molecule. That means each water molecules are tetrahedrali surrounded by 4 water molecules like diamond. It's like a diamond crystal. And diamond crystal, the packing efficiency? 32%, 68%, 34%, 66% are vacant. Ice crystal, like diamond crystal, 66% are vacant. Interstitial space, void spaces, large void space. Rigid hydrogen bond, each water molecule tetrahedrali surrounded by 4 water molecules. That's why the density of light is too much less. It will float on water. Density of ice less than liquid water. Now we got some example. Very little example I have given here. I placed here. Simple example, a simple application of hydrogen bond. But in your syllabus, whole organic chemistry and biochemistry, you will get great application of hydrogen bond. Without hydrogen bond, we can't think the bioprocess as well as organic chemistry. Now stay with us. When we discuss biomolecules or organic chemistry part, there you will get a great application of intermolecular and intramolecular hydrogen bond. Thank you to all and stay with us.